Hopefully I'm not going to screw this up.
Go ahead, I got it.
I'm too fat. Well, I went running this morning.
There you go. What's your face in front of me?
I know.
Don't talk about anything weird. We're on video.
It's recording already.
Yeah, so don't talk about anything weird. Just everybody will hear it. Like that girl you got a crush on?
Oh, she's in this class. Whatever, peeping Tom.
Oh! Don't go there. Where's Owen? I was waiting for this dumbass.
You didn't see him outside the building?
No, I waited up for him. I think he took the other stairs and like went through the basement or something.
Maybe.
Did you take the other stairs?
What was that?
Did you take the other stairs from Burnham?
No, I had to go to the bathroom.
Oh, I was waiting outside for him. Like,
Oh, were
he
you?
has to come out sometime. If he took
Yeah,
the
I
other
was gonna
stairs,
say something, but there's too many people, so I'm like, when you gotta go, you gotta go.
yeah, I guess so. But don't say anything too weird because we're on film. Let's talk about your rendezvous you got going on tonight.
Yeah, I'm getting on my room.
Let's say that on camera.
Sorry.
Alright.
Probably gonna make him my GF, but
Oh, you're overly excited.
yeah. Probably
Don't put it on the pedestal. You might not work out. You might be bummed for like 2 months. Yeah, I guess so. It's risky not to take risks, right?
Yeah. So wise.
You're learning.
We got your wisdom on camera,
Yep. See?
so I can play it back over and over again.
Just listen to it.
Yeah.
Give me a piece of that gum, please.
Yes, of course, dude. Smells one too.
I heard gum. You saw my.
I got you.
Like, so yeah, pike ears and shit.
I know, there's like.
Look at him, he's got gum.
Thank you.
So if I get your attention, please, does someone know how to turn that freaking light off? I have no idea how to do it. It's messing with the lights in this room, and I cannot figure this freaking thing out. It's awesome. You know, they do have a lot of nice stuff in here, I have to admit, but we're gonna have to live with weird lights. You guys don't mind. Don't worry, it's just me staring at the blue
It's
light.
fine.
Take a piece of paper over if you want.
I don't worry about it. Okay, folks, so you got your homework, and video is up. I noticed, so class business as usual, I noticed there was actually an extreme flaw in the calendar. I just noticed it. Let me tell you some things that happened. Like, I feel, and I'm going to say this on camera, hello, Bill Gates. Microsoft Windows, it just sucks. I mean, they've changed it in such bad ways that it's almost unusable. What it's doing lately is that, you know, it caches, your computer stores copies of files so that it can open them faster. Well, it doesn't update them. So when I change a document, like videos on Thursday when the video is finally processed, I take the HTML file where I say, hey, there's a new video, and I upload it to our server. Except that it didn't allow me to do it. It sent the one in the cache, which was not updated. And so nothing was updated, and I didn't realize that. It did it with the calendar. When I was writing the calendar before class, I had two versions. One was just kind of hypothetical, and the other one was the one I actually wanted to use. The one I wanted to use was written second, so when I uploaded it, it sent the first one, because that was in the cache. So the calendar was completely wrong. So anyway, if you have copies of the calendar, if you're reading ahead, probably not, whatever, it's fine. The calendar is completely wrong, I just discovered that. So when things screw up, or homeworks aren't posted, it's because this is happening. I'm aware of it, but sometimes I screw up just because I assume it should work the way it should work, and it just doesn't. So anyway, sorry about that. Other bits, because we really got started already a little bit late. The camera, again, this will be uploaded. It takes nearly 10 hours to process because we have 2 lectures today. About the 2 lectures, I said this before, this is our second problem-solving hour. Okay, not good. Now, it looks like all of you are here. I'm not going to do it. I'm not going to do that, right? Because, all right, so you're going to have Wednesday homeworks, right? So I'm going to try to cover Wednesday, Friday, what you will need to do the homework that's due the following Wednesday. Sometimes it bleeds into Monday. I try not to do that. All right, now, if I begin now with problem solving, then I can't talk about the problems to be solved, which I cover in the next hour, right? And that sucks for you. I mean, it doesn't matter to me. I've got all these lectures already written. It doesn't matter which order I do them in, but I think it matters a lot to you. So what I'm going to do is this hour will be lecture hour, and I'm going to use the following hour, which is the actual lecture hour, I'm going to use that for the problem-solving hour. And to be blunt, look, you're supposed to be here anyway, so I don't know why it would matter. It's only in your favor. If, however, you just don't like that, because to be blunt, sometimes people like to just say, well, I'm just going to blow off the problem-solving hour. Well, the problem-solving hour is going to be the second hour, the lecture hour, because this is in your best interest. But if you really don't like it, tell me. And we can do a doodle poll or something, and I can switch it back if that's what you want. But I wouldn't recommend it, right? Because, you know, if it doesn't matter to me, I'm only doing this because I think it's going to help you. So anyway, all right, regular lecture, 10-minute break, smoke them if you got them, don't smoke. Actually, you can't smoke, huh? What are you smoking? God, when I go by the dorms at night, anyway. I really took it up a minute. Smoke-free canvas, 10-minute break, you know, take it easy. My camera actually has to recharge. I need that 10 minutes to recharge the camera. It only goes 50 minutes, and so there's not enough juice to go for the next hour. It only needs 10 minutes to recharge. So I'm going to leave that here. If you guys can just, you know, not steal it. Don't let someone else steal it. You want the camera, right? So, okay, so anyway, blah, blah, blah. Monday, no class. Now, Tuesday, Wednesday, when all of you were scrambling to actually do your homework, I have office hours. That's why I have office hours on Tuesday, Wednesday. I don't like you to procrastinate, but most of you are. I mean, it's just a reality. So some of you will be scrambling to me on Wednesday, 12 to 1, to help with your homework. That's fine. I wish you would have started earlier, but you're going to do what you're going to do. All right, so again, Tuesday, Wednesday, office hours for your homework. Now, a lot of you said, which one? The one I emailed you all. If you're not getting my emails again, email me. Number 7, was that right? Okay. You're getting confused by, I said, the volume of a gas is reduced by 1/3 of its initial volume. By 1/3 of its initial volume, not to 1/3 of its initial volume. If I had said 2, that means that V1 was reduced by 3 to get me V2. But I said by. It's a star. And that means that V1 was reduced by 1/3 its initial volume to get to, sorry, an idiot, to get to its second volume. Okay, do it that way. It's actually very easy. I just kind of I'm getting you to write down equations based on words. That's really the purpose of this question. All these questions have purposes. And this is what this one's purpose is. You're going to get a lot of questions, math questions that come in the form of an essay. So you've got to be able to roll with that. Now, I can tell you this, if this was on the test. Now, I am grammatically correct that this is correct. You can say, oh, that's open to interpretation. No, not really, I'm right. But I can see how you can make that mistake. So if this was a test and half of you did this because you just weren't following the words, I'd count it right. I realized it was a very simple mistake. About 1/3 of you, English is your second language. I know that. And I would actually realize that it was difficult to interpret, and I would look at that and do it correctly. That's also why I get hints, which are answers. Look at my tweets. Are those a bunch of random zeros and ones after all? I don't know. But this is why I get hints, because I can't work with all of you individually all the time. The hints, answers, are to guide you. Because it doesn't matter whether I give you the answer or not. You still have to work the question. And that's where all your points come from. You write down the answer, I don't count it correct. On the test, people be warned. I had people, me about this, they're like, hey, I had the right answer. And I'm like, yeah, you had a 10-step problem and you just wrote down the answer. I wonder where you got the answer from. Oh, come on. Now, I'm not going to accuse someone of cheating, but that's pretty damn questionable, so I'm not going to count any points on that. So just be forewarned. It won't be a problem, right? You're going to do the work on your own, and the work will be there. See, there's no issue. Okay, I am really running my mouth, and I have just wasted almost 10 minutes. Okay, we talked about PV equals nRT, non-ideal gases. Okay, this is when PV equals nRT does not work. This is everything, right? Now remember, we talked about last time, I don't want to spend time reminding you what PV equals nRT is, but Dalton's law. Dalton's law was a hell of a thing. Dalton's law says it's only going to work remember that I can put 3 gases in 3 balloons of the same size, and it's the same thing as if I put them all together and add the results, add the pressures. Right? That was Dalton's law. But that only works if things don't hit each other. They have to have mass. I mean, you can't get rid of that. But one of you correctly surmised that if it has mass, but they still don't hit each other, it has no volume. Perfect gases have no volume. They also don't interact with each other. It's just a little other thing, whatever. And that's not true. And that's why PV equals nRT does not work. Your homework problem, by the way, that methane problem, those are real numbers. You know, it's kind of tempting for me just to make it up, like, okay, the pressure of methane is 5 atmospheres. I can just come up with stuff. I don't like to. Sometimes I will, all right? But I don't like to. The pressure, temperature, volume, or whatever I gave, those are real numbers. It's actually almost the condensation point of methane. That's why PV equals nRT really doesn't work. So you have to treat them as non-ideal gases. Okay, let me draw what that looks like. And this is, okay, I know I should PowerPoint or bring slides sometimes. I'm just opposed. VM. Now VM is the volume per mole. You're going to see VM a hell of a lot, so you might want to write that down. Okay, this is in atmospheres. Now, you don't really need to worry about these numbers. It's just I want to give you something real. And what you're going to have at 50 degrees, I may have exaggerated that a little too much. This is CO2. Okay, so this is the normal, I remember which one was it? Charles' law? Yeah. No, Boyle. P is proportional, PV is constant, therefore P is proportional to 1 over V, which is basically 1 over X, and that's a 1 over X curve. All right, now let's go down to 40 degrees C. Again, I know I'm drawing data, it's not perfect. And I showed you last time that curves can bend a little bit, and that's not just my wrist getting Parkinson's, right? That's real. It bends a bit. Now, the perfect gas equation has P proportional to 1 over V always. You can't get inflections like that from 1 over X. So this is a deviation. It's deviant. She was pretty. Anyway, and then at 31 degrees, you did this. It flatlines like a heart attack. And what that is a critical point, and that's the temperature at which, above this temperature, right here, and don't really write this down, I don't care, it'll come up later. Critical point. And I'm just going to say it, I don't want to write it down because I don't really care. Above the critical point, you can't have gases and liquids ever together. It's all gas. Actually, it could also be a critical fluid. That's coming up. That's not even worried about it. Below the critical point, you can have liquids. Above it, they can never form a liquid. Okay, now, as you can imagine, I'm going to throw equations at you that do this. Right, that's coming up. And we're going to do a lot of crazy stuff with them. It's all algebra. It's really not bad. There really isn't that much calculus in this class. And what calculus there is, I'm covering in the next lecture. Okay, now why is this happening? So why? HCl. Gas or liquid? Yeah, gas. So what you do is you bubble it through water to capture it, and that's your, 31% roughly HCl. Why not higher? Well, you bubble more HCl, it just bubbles right out. So HCl is actually a gas, and I've seen gas cylinders of it, it's really kind of scary. You actually have to have a license from the fire department to have it because, it's really easy to kill everyone. Okay, so let's think about what it looks like when a body meets a body running through the ride. You're going to have a proton. Oh, right, that's a hydrogen. And it's going to be connected to a chloride. I'm trying to draw these kind of correctly. I don't know if getting the atomic radius is exactly right. Now, the thing about HCl, it's got a pretty good dipole. Okay, what else? But it partners up to someone. Just because they're just flying around, they just happen to run into each other. Cl minus and H plus. See that? Dipole, dipole. Dipole, dipole interaction, right? Remember this, this thing, right? Dipoles they're like magnets, right? The north likes the south and all that. Not the war of northern regression, but you get my point. There's another way to do this. This I call a dog maneuver. They're basically sniffing each other's butts. I just moved to University Village, and there's just nothing but dog owners there. So, I'm surrounded by other people's dogs. Okay, so you can do that too. And there's an obvious electrostatic attraction. Of course, they're fuzzy and they kind of like each other. It's the north-south pole of magnets. They're going to try to move towards each other. But they also have a lot of kinetic energy. I mean, they are gases after all, so they may not hang out with each other for long. But this is why, two things come past each other and then they'll do like that. That's what they're doing. They're changing each other. And sometimes and if they really are pointed the right way, they're really attracted to each other, and they aren't going in the same direction, they will smack into each other. That's in a minute. Okay, and so, I do know why a dog does this to your leg, actually. It's trying to establish dominance. Anyway. So, this is dipole-dipole. And you had, God, my handwriting is bad today, sorry. You had this in physics, and let me just remind you that, I'm sorry, I don't know. The energy of interaction scale says, and I'm going to put a minus sign. Normally you say it scales of 1 over r to the 3. You think of dipoles as being very small little things, and so point dipoles, so the distance between the dipoles has a certain energy lowering property, which is scaled as 1 over r to the 3. I put a minus sign to remind you that energy going downhill is good. And that gets kind of confusing. Remember, delta G needs to be negative or it's not spontaneous. That's coming up. And why? I'm actually going to give you a good theoretical underpinning of why energy going downhill is good. Right? That's why something is spontaneous. Now, if you forgot where it came from, I don't want you always just to say, okay, yeah, I think I remember that. No. Coulomb's law, right? 1 over r. And positive and negative, right? That's 1 over r. So when you have this situation and you apply Coulomb's law to all partners, and then you take certain limits, you get 1 over r to the 3. And minus because energy is downhill. So I don't want you to, always presuming things. Okay, can xenon, which is a ball, can xenon be attracted to xenon? It's a fuzzy little ball. Can they attract each other in this way? Well, okay, hold on. They can't attract each other in this way because it's a single little round object. But can they attract each other? Yes? Yes, they can. How does that happen? Okay, I'll do this. This is a lot more common. HCl is not like really floating around our atmosphere very much. But let's draw xenon. And xenon's a big atom. That's going to be one of the answers to your homework problems. It has a big, thick nucleus, and it has a whole bunch of electrons. And I don't know, 300 electrons? I don't know. Now, here's the thing about quantum mechanics. This is the outermost electron. I'm just going to draw it that way. Okay, 346. Now, I know you engineers aren't taking 346, but you chemists are chemists, sorry. So when you take 346 and you do quantum, you learn about s orbitals and p orbitals, and you're like, this represents where the electron is. And it's like this, like an s electron is like it's a ball. So the electron's in a ball. No, that's not the right interpretation. A wave function, when you see those s orbitals, which you had in freshman, inorganic, that represents where the electron might be. You're not allowed to know where it is. But here's the thing, it is somewhere. It is an object. And actually, like string theory, like Stephen Hawking stuff, I learned that string theory is actually when you give an electron size. See, normally us chemists say that an electron is a point, and a point has no volume. Anyway, I just thought that was neat, but anyway. Okay, so now how does this part work? Okay, here's another xenon atom, and again, this electron is somewhere, and two xenons can butt up against each other and do this. The electron is somewhere. I don't know where, but it is somewhere. Look at that. Now I've got my attraction. It's not strong because these electrons are whizzing around very quickly. But when they get close to each other, it's kind of nuts. They know it. They know that they're nearby each other. And this guy will adjust its electron, and this guy will do the same, such there's a little energy lowering interaction. And they do that on their own. And I have no idea why. Ask Stephen Hawking. I don't know. But so this is instantaneous dipole. I am struggling to remember how to spell this. I hopefully got it. God, my handwriting is terrible. Sorry. Instantaneous dipole. Don't remember this, but you may have remembered this was called the London force. I don't remember this stuff. I don't care what it's called, as long as you just kind of get it. Now this guy is fairly dominant. It scales as -1/r⁶. Okay. Anyway, so what? Anyway, so what is that things attract each other, and that's important, and that's why I get those inflections in this thing. Energetically, what does it look like? This is called a Lennard-Jones. Lennard-Jones potential. Again, you will not see that word again in this class. It is called a Lennard-Jones potential. I'm telling you that. I don't care for your ability to memorize people's names. I call myself Dr. Chicken. So anyway, so this 1/r⁶, 1/r⁶. It's no matter what, it kind of looks like this. So this is the distance between two xenons, distance between two HCl, or an HCl to xenon. It's always downhill. Okay, but something tempers that. So why don't things just crash right into each other? Why doesn't an electron just kiss that nucleus? Why not? It's right there because of this. Okay, so okay, this is a quantum mechanical principle. This is called exchange. Okay, let's let those two xenons get closer together. All right, plus E. Okay. Okay, now they're getting too close. Okay, but doesn't this look better? Doesn't this look much better? I mean, look, the electron's even closer to that nucleus now. It's got to be happier. Now quantum mechanics kick in. And the quantum mechanics is something called exchange. And again, I'm always going to be previewing quantum because it's really freaking hard, so just prepping your mind for this. Exchange says that this is bad energetically, extremely bad, like exponentially bad. This is 1/r⁶ good, but this is exponentially bad. The reason is that as this electron invades this electron space, they're starting to become quantum mechanically identical. They're in the same space, they're beginning to have the same state. Now, exchange comes from the Pauli principle. Remember the Aufbau principle, how you had to draw up electrons on your molecular orbitals, and then you do down electrons. Remember doing that? And then you went to the next highest orbital when you were doing atomic structure of atoms. The reason that you had to do that was because of exchange. You can't have two up electrons in the same orbital. It just doesn't work that way. I am trying to, when these things hit each other like this, I'm kind of starting to do that. Two up electrons in the same molecular orbital. You can't, but it's trying. So energetically, they get blown apart to prevent that from happening. And again, it's an exponential. So it's like that. It's really hard. It's hitting a wall. They're hitting each other. And you run into a wall. You run into a wall. You wake up at night, you got to go, and so you're walking around in the dark, you hit your nose. It sucks. Anyway, so the Lennard-Jones potential ends up looking a lot like this. Anyway, it's a relatively thin. Let me do this a little bit right here. It's going to kiss the R⁶ pretty quick, or R⁶. There we go. So that's what it looks like. And if you ever do any kind of computational molecular modeling, you're going to have one or Jones stuffed up your ears until you're sick. So anyway, okay, so this is why I didn't draw that very well, did I? Okay, so this is why things are non-ideal. And let me, before I change boards, let's do this. Let's write a Taylor series. Okay, so now I'm switching from pictures to mathematics. So I have kinks. I have nice 1 over x behavior for the most part, but then I'm seeing these kinks. Now, a way to fit a line, and you had this in Calc 1, I know I can fit a line with the Taylor series. I can literally fit just about anything if I have a Taylor series with enough terms. That's what a Taylor series is, that's why we have a repeating. Don't, look, okay, if you don't remember what a Taylor series, this is a Taylor series. What I'm going to do is have a polynomial expansion with, fitting parameters that make it work. And that's going to be, I think I'm still going to, NVM, sorry, I should have done this, volume per mole. Sorry, I'm presuming that's not true. Okay, we're going to do everything with VMs, by the way. So whenever you work a problem with VM, remember to take the moles I give you and take the volume and divide it by the number of moles. Don't ever screw that up. It's a good way to screw up a question. Okay, so I'm assuming I'm still going to have ideal gas behavior, but then I have higher order terms to get to those kinks at those weird temperatures. And to do that, I'm going to have to pick a variable in which to make the expansion. This is called the virial equation. And it's expanded in terms of volume per mole. We have this V fitting parameter, which is a function of temperature. Okay, and that does a lot of good. That helps a lot to get to those weird kinks. And then I've got a C parameter, which is also a function of temperature. Now, the Taylor series has your expansion variables always increasing in power, in case you don't remember. Well, there it is. Now, we could go on and on and on, but you engineers, you're the guys who came up with this, it generally stops right there. Usually people stop at the V parameter. C parameter is pretty good. So it's very important to remember that B and C are T-dependent. Okay, and there are, I found one day when I was a grad student in Berkeley's engineering department. I found an encyclopedia-sized book. B and C parameters for almost all gases is a function of temperature. And so it's just a huge table. Now that makes this very accurate. Okay, and so what about that? Well, if you're designing a power plant and you engineers, yeah, you're going to do this stuff, especially when you have to do your senior project, which maybe you're right now. If you really have to design a power plant and you've got expanding water, because that's how we do it, you really need to know what the freaking pressure is, right? Because when you do that homework question I have on methane, PV equals nRT is freaking way off. It's like a factor of 3 too high, something like that. I just gave you the answer. But anyway, but this guy is very accurate, especially if you go further and further. And so that way, you know how much heat you put into the water, you know how much steam you got, you know the volume of the turbine, you know the temperature, now you know the pressure, now you know whether it's going to buckle or not. And that's really freaking valuable, right? What I don't like about this is that there's not much insight. So not zero, but little. What do I mean by that? Hold on one second, let me just spell this. This is a bad speller. It's gotten worse over time, but anyway, that I'm blind with that. So it doesn't provide a lot of insight into molecules. I, as a physical chemist, am not an engineer. As a physical chemist, I don't care much for that because I'm not going to build a power plant. Everyone would die. So I like a different equation. This is just one example. You engineers love this. Like what's that? Payne Robinson. There's a couple of types of equations of state. There's several equations of state. This is one of them. This is a good one. The one I like, though, I'm going to cover in a minute. But here's the thing I want to do. I want to stop and do a homework question, and then we're going to do a test question. Okay, I am obsessed with units. I can't help myself. I think units are very, very important because sometimes when you don't understand something, getting the units will kind of get you to see it. And you need to see it because I'm going to test you on it, all right? There will be times you're going to have an equation, and I can say, what does this part do? Why is it there? Right? It's not just a bunch of meaningless dribble. And if you get stuck when you have that on your test, if you tell me what the units are, I might give you half credit. But you know what happens? You get the units right, then you actually say, oh yeah, wait a minute, right, that's in liters per mole. That means that it's this. And now you got 100%. Okay, remember the principle. Things add to the same unit, things multiply into different units. All right, RT. Someone? Energy per mole. Joules per, let's do joules. Joules per mole. It is energy per mole. Horsepower per water. I don't know. Okay, joules per mole. Okay, joules per mole times the number what? Joules per mole. Numbers don't have units. Okay. Now let's go here. Now let me just start off before I ask you, if B has no units, which is possible, then this term has joules per liter, right? Joules per mole times moles per liter, it's inverted, is joules per liter. Joules per mole, joules per liter if B has no units. That don't work. Remember, that is physically, I certainly can write equations that do that, but they will not correspond to reality. Okay, so now, what do you think? What do the units be?
Meters per mole.
Liters per mole. Liters per mole, canceling this one out, giving you something with no units, which is correct, just like this. Here's a trick, and I'm going to have this on the test, and I'm going to have it on the next homework. Yes, you have units here, but you can kind of separate that out. And just look at this. This is a sum by itself. This has no units. This, therefore, must also have no units. And you can even forget the RT. Or you can, and you can still get it right. It doesn't matter. This is just a shortcut. No units, no units, no units. So you can also figure out what C, obviously meter squared per mole squared. Anyway, expect that. It's important. And hell, I'm the teacher. I get to decide. Go get a PhD through a postdoc. Be an assistant professor for 6 years. You get to decide what class, but it's actually soul crushing. I wouldn't do it. But okay, now let's do the van der Waals equation. And this is one, it's on the test, it's on the homeworks. You're going to see this over and over again. I love the van der Waals equation. Okay, so here's the van der Waals equation, and it does a lot of really neat, things. Equation in shorthand. And I'm going to give you the long form, then I'll give you the short form. So pressure, nRT over V, perfect gas law, and van der Waals made an adjustment, minus NB, and then B is a fitted parameter, minus A, N squared, and that's still moles, E squared. Yeah, okay. A is another fitted parameter. And you're going to be working this guy on your homework. A better way, so be careful of this. P is RT over VM minus B. I've just divided everything by N. 1 over N, 1 over N, top and bottom, minus A over VM squared. This is nicer, it's like memorizable. You don't have to memorize it on tests. It's on the cheat sheet. You have a cheat sheet on the test. I sent it to you the Wednesday before the exam. So I don't know why you love that stuff. All my classes wanted that. Okay, so what else? So A and B are fitted parameters, but they are temperature independent. Okay, and that unfortunately makes it's less accurate. It's less accurate as a result. Well, you know, it's not bad, by the way, but it's not quite as accurate as imperial. Of course, I'm saying imperial. It's obviously better than B equals MT. It provides insight. Van der Waals won the Nobel Prize for this, by the way. And we're going to break this sucker down into all kinds of little pieces and understand it completely. And we're going to do this for the next 2 lectures. Including this one, so I run my mouth like a moron. But so we're going to do a lot with this. Understand everything about non-ideal gas behavior. By the way, Van der Waals said, oh, why didn't we divide by VM cubed? because that's completely wrong. And that's one of the things you're going to prove. Well, why not A over VM? Completely wrong. You're going to prove that. It has to be 1 over VM squared. So A and B, again, are the parameters, temperature independent. Huge insight when Vanderbilt wrote this down, and it wasn't something he just said, oh, I guess this works. No, he spent, it's like a couple of pages on Wikipedia. If you look at the derivation, it has an actual real derivation. It's freaking huge. Even I can't follow it. So he writes this down. He wins the Nobel Prize. Why? Because you can actually understand molecules from it. You know, I got gas in the balloon, so what? Well, I analyze it with this, and I can actually know how big the gas molecules are. I'm going to do that right now. So he won a Nobel Prize. That's pretty cool. Just for writing this down. Not that it wasn't easy. Okay, let's see. All right, now we all want to figure out what A and B are. Because they're going to tell me that molecules exist, they're going to tell me that they have volume, they're going to tell me that they're attracted to each other. Okay, so, mystery B hour. What is B? Let's see here. What I'm going to do is I'm going to start I'm going to bug you with this thing. First thing I'm going to do is multiply everything by VM minus B. Okay. VM. I can hear you. Guess what? You're going to know your name one day. Pretty soon, actually, I almost get to know everyone's names. When I take your test from you, when you're turning them in, that's actually how I'm knowing your name, by the way. So anyway, okay, whatever. All right, I've done a step. Childlike algebra, middle school. Not hard. Okay, now what I want to do is I'm going to take this term and bring it over here because they contain a common factor. So I'm going to retain VM minus B, but I'm going to bring that A factor over, which is going to be P minus P plus. P plus. Bringing over negative is a positive. Okay, now I know I've done 2 steps. I brought this over and I factored, but I think you can handle that. 2 algebra steps. You're lucky it's this easy. And what I'm doing, by the way, I'm trying to isolate B. I'm trying to say B is equal to what? And then I know what B is. If we're going to do that, let's see, what am I doing there? I'm going to first divide by this term. And so that part goes away. Oh, my handwriting is naturally getting bigger. Okay, I'm left with VM minus B. And so what I'm going to do is I'm actually going to keep VM and bring B over here. I know it's kind of like the opposite of what I said. Just hold on one second. I'm almost there. Sometimes derivations kind of go in weird directions, but then it totally works. I think people actually always know the answers before they do the derivation to guide them to the derivation. I don't really know that, I wasn't born in 1800. So, okay, now this is what I got. This isn't very useful. What we're going to do, and several more times, we're going to take a limit now. And we're going to do, okay, I'll write it here. Sorry, I know my board working is a little bit odd. Limit of P going to 0. And by the way, pressure goes to 0. Wait, no, sorry. I'm going to pressurize it. So I'm going to raise the pressure. And that means VM is going to go to, VM's going down, P is going up. Right, so I'm going to pressurize this gas. Sorry, I got a little jumping ahead. That's the next derivation. Sorry. Okay. All right, now, P is getting huge. And God knows we have machines that can pressurize things to unbelievable levels. We have, I actually used to work with one. I was freaking terrified of the thing. I had this big, huge pump that could raise something to 100,000 atmospheres. Again, you had to have a license from the fire department to have it. And now here's another neat thing. We have these things called diamond anvil cells. It's like this little, looks like a little triangle, and it has 3 knobs, and 2 diamonds are built into the plates, and they have the very, the nice diamond tip. The tip is chipped off, and so they're squeezing against each other. And you just pressurize it by turning the screws. You can pressurize the stuff in between those 2 diamonds. You can pressurize them to that above the pressure of the interior of the sun itself. You can do it with your fingers. It's kind of cool. God, this is how I waste time. So let me tell you something else. I know this guy he works at this place called the Carnegie Institute, and what he did was on a whim. He studies high pressure reactions. He got cells, E. coli cells, and he put them in this diamond anvil cell, and he pressurized them. Squish. But, so he opens it back up and most of them are dead. But some lived. Now remember, this is tremendous pressure. Some of the cells lived. He cultured them. He put them back in the diamond angle cell and he squeezed them, he opened them up, they all lived. That's that. He said he proved evolution. And I stood up and I said, you've proved intelligent design, sir. Oh, come on. Anyway. So we can pressurize things. My point is, we can pressurize things to shockingly high levels. It really is kind of cool stuff. All right, now this is a big number, plus 1 over a very small number. What's 1 over a very small number, especially a very small number squared?
Infinity.
Well, say it's a big number. Okay, you know, just because I pressurize something doesn't mean it's hot. You know, my little diamond angle cell, it's still room temperature. Yeah, I know when you're starting to pressurize something, it'll probably get hot, of course it will, but it can cool back down. So this doesn't have to be huge, but this can be made huge. 0. All right, the limb. So, sorry, I wasn't really doing proper mathematical notation there. A pressure going to infinity, Em is equal to B. Okay, now I ask you this. Phenomenological. Let's think about what happens. I pressurize a gas. What happens eventually? Remember, I can bring it to the sun. Pressurize a gas, what happens? It's going to turn into, I pressurize the liquid, it turns into, all right, I keep pressurizing it. Can I go on forever? Right? If I put a piece of iron between a diamond angle cell, no matter how much I pressurize it, can I just squash it out of existence? I don't think so. There's a limit. What do you think the limit would be? Think about the atoms. Right? So I'm going to pressurize something to an unbelievable level. There will still be a volume in between those diamonds no matter what. I cannot go beyond a certain limit no matter what. The diamond's crack, I don't know. What do you think that volume is? Yeah?
Well, it's like the length of like one molecule.
Well, yeah, the distance between the two diamonds would be like the length of the molecule. It's the volume inside of it is the volume of the atoms themselves, right? Because you know, when you have a solid, most of the volume is occupied by the actual size of the atoms, and especially when you give it a really big squish. All those little spots in between, you know, you think about hexagonally close packed. You've seen some of those pictures if you had an organic. I think most of you had an organic. There's not much space in between those atoms. Most of the volume is that of the volume of the atoms themselves. So that's what B actually is. B, sorry, not looking at the board very well. Oh hell, let's go to the other board. So B represents the volume of atoms, right? And we know that atoms have volume. Now PV equals nRT says that they don't, but that's wrong. Van der Waals simply, look what he does. He takes the volume and he shakes a little up. Now that's the volume of the balloon. But Van der Waals says, well, that volume of the balloon isn't the real volume because some of it has been taken away by the atoms themselves. So that's what he did. So D is equal to volume of atoms. And for examples, I always like to stick with helium or xenon because it's just easier that way. And so anyway, I hope that makes sense. Okay, 5 minutes, then we'll take a break. I might go a little bit over because I really did waste some time at the beginning. I'll just do the A. So what is A? Okay. Yep, so I'm going to write the Van der Waals equation again. Minus B, and I've got to memorize at this point because I've taught this 10 times. The 4th time I did this class, I actually showed up to class without my notes, and I just did it anyway. Some hoops, man. Anyway, let's do the limit. See, this is why I got confused a minute ago. P goes to 0, and Vm goes to infinity. So anyway. All right. Okay. Now, if that's the case, now, if you haven't looked at the homework yet, and actually I will write down some numbers, a parameter, given its unit and given the magnitudes, and this comes from fitting data, the A parameter is rather largish for a number, given its units. The B parameter is rather smallish for its magnitudes, like always 0.01 or something, moles per liter, liters per mole, right? half liter per mole. That's a liter per mole, this is a liter per mole, and there's a summation. Sum of the negative thing, right? That's a subtraction. So this is tiny. This is tiny, this is now huge. So I choose to get rid of it. So, and again, I'm sorry, I need to use proper mathematical notation. I wasn't a minute ago. Here, I think some of you might have some trouble seeing. P is equal to RT over VM minus A over VM squared. There's nothing obviously to subtract this from, it just stays as it is. Obviously, it's a large number, it needs to stay there. Okay, RT over VM, you recognize that? It's something else. It's going to come up a couple of times, it won't be in your test probably in some form or another. RT over VM. Pressure, what kind of pressure?
Ideal gas.
Ideal pressure, right. Of course it is. PV is an RT, so PVM is RT, so P R is equal to RT over VM. So this is P, and I'm going to call this not ideal pressure. We have to put a little not, meaning it's the ideal result. So it's just easier that way. So what? Watch this. This is kind of neat. And you know, we have two things that make a perfect gas not perfect. It's volume, which we just covered, and, wait for it, goes to 0, right? P minus P naught is equal to minus A over VM squared. Okay. The real pressure minus the perfect gas pressure is a negative number. By the way, from fitting the van der Waals equation to all the gases that we could get our filthy paws on, A is always positive. There's no negative A's, there's no way you can have a negative B. Atoms don't have negative volume. A's and B's are always positive. Never seen a violation of that. You get used to this. I really like it when you tell me whether something goes up or down. It's, you know, trends. Trends are important. This is always negative. Okay, so the ideal pressure is always bigger. The real pressure is always bigger than the ideal pressure, right? Right? Isn't that right? No, it's negative, right? That's a smaller number than that one. So the real pressure, so therefore, the real pressure is always less than that predicted by the perfect gas law. Now, look, I mean, this is, the van der Waals equation is not perfectly accurate. To tell you, let me know, it's not perfect. So this may not always be true. But it's pretty good, all right? So for the most part, like 99% of the time, this is going to be true. Okay, now what this is doing, so what does the A do? The A takes the pressure and reduces it. Because it's also kind of the same thing as taking the volume and reducing it. It's kind of the same thing. So it says your real pressure is not as high as you think. Now, first day, what's the source of pressure? What was my phenomenological model?
Molecules colliding.
Right. So when I was younger, I would like take something and throw it into the audience. I kind of got in trouble. So, right, things hitting the wall. Now they're not hitting as hard, right? They're not. The pressure's gone down. Why would they do that? Okay, think of the galaxy. What holds a galaxy together?
Gravity.
Gravity. The stars are attracted to each other by gravity, of course, not in this case by dipole and induced dipole interactions. Right, so what you're seeing is, therefore, A is molecular interactions. So almost all molecules have very significant interaction. I remember those xenons, I could have drawn it such that they were repelling each other, but they won't do it. They're smarter than that. I never could really understand why, but it's just how nature works. Two xenons, when they run into each other, are going to rearrange their electrons to induce dipoles such that they're happier with each other, and they will always do that. There's no violation of this. And so that reduces the pressure. Think of it like gravity. The things are trying to hit the wall, but they're kind of stuck to the interior where all the other molecules are. They're kind of like sheep. And anyway, so there you go. Your A and B tell you this is why the guy won a Nobel Prize. B tells you that gases do have volume, and A says that they're generally attracted to each other. Let me give you a little bit of trim because I've now hit my limit, unfortunately, and I really was supposed to tell you some other things. Next lecture, I'm going to have to go a little faster on Wednesday because I'm a little bit behind now. But what do I want to say? Okay, now it turns out that the A parameter is almost always dominant over the B parameter. What I'm going to cover next time is A pushes and B, so, no, it's better to say A pulls, B pushes. They tend to work against each other. However, A is usually dominant. So I mentioned before, B is a small number because it's the volume of an atom. A, if you look at the numbers in the table, like you do on your homework, A's tend to be kind of big. So A's tend to dominate B's, except for hydrogen and helium. They are the oddballs of the planet, of the universe itself. In their case, the A parameter, because, they're so small, remember like hard and soft atoms, they're hard. They're, I had a hammer and I could hit a hydrogen atom, it's gonna boom, and break my arm. Other things, not so much. So a steel ball is hydrogen and helium, a rubber ball is everything else. So for them, the A is very, very small, and it's just unusual. Everything else, A is very big. For hydrogen and helium, B dominates. And so hydrogen and helium always do weird things that the other gases don't. And, God, I still want to keep talking, but you need a break, and I need a break. I need to get a shot. Okay. All right, so I got to recharge the camera. Let's meet back in 10. I'm just going to go upstairs for a minute.